dimension mark. No. So, any questions? So the last topic is what I announced. It is singular value decomposition. It's not an easy topic. So probably what we saw so far probably requires, depending on it, 3, 4, 5 weeks. So we are going fast, and we don't define everything we speak about. Certain things I need to know already, and it's even more true. So I don't prove everything very much. But it follows a little bit the book of Professor and Bao, not sure if I pronounced it correctly, maybe in algebra, where they try to introduce these stuff to make features and interpretation. But the other way to think of the single value composition is a way to given a matrix, so it's applied to a matrix, represented as the composition, the products of simple matrices. Very much like the eigenvalue composition. The eigenvalue composition, you take a square matrix, must be symmetric, right? And then you can write it as an orthogonal matrix times a diagonal matrix with the eigenvalues and diagonal times the transpose of the orthogonal matrix, which are the two vectors. And here, you do something similar. However, it is done to a generic matrix. It doesn't need to be square, doesn't need to be symmetric. It always applies. So, you give me any real matrix, I can write it as, I can derive this singular value composition. So, okay. And it is important because supervised learning, for example, you speak of principle of component analysis, it is based on SPD, squares, as we see in supervised learning, can be better understood by using the singular composition, spectral clustering, another method that you might see in supervised learning. Also requires the eigenvalue composition. Then we have low-rank matrix factorization, which is used, for example, in collaborative filtering, recommendation systems, also using singular composition, and many more. So it is useful quite broadly in data analysis. So I would say that it is important to read a little bit about it, and try to develop some intuition beyond pressing a button in Matlab. Which is very important, of course, because in Matlab you can have a system which gives data, components, stuff like that. But what is the meaning of that? Then, in order to understand the meaning of that, you need to play with the data and do some practical exercises, but also you need to abstract a little bit and understand what are you doing as a computer. And so, what it's doing is something complicated, it's doing some power method, some iterative algorithm which computes the single value composition, but that you don't need to worry about. But what, for example, you can start to think about is this picture. This is a little picture which is also so small, it's difficult to read, unfortunately. But hopefully the notes it is better. So here you take a matrix A, and I take it to be a square matrix. And so what happens is that if you take the unit circle in the plane, which is the unit circle, right? You take any vector in the unit circle, and you see where it is transformed when you apply A. So which other vector you obtain by applying A. Right? Since A is a square matrix, A of x, so x is any point here, will be a point in the plane. Plane in the upper space, the codomain, right? Now what happens is that this unit circle is always mapped to an ellipse, which is tilted. Right? But this is a fact. Right? More generally, if you are in higher dimensional spaces, you take a hypersphere, which is a set of points which are normally equal to 1 in the first space. This set is mapped to a hyperellipse, which is the extension of the notion you see here. Let's not worry about that. So what is the important message, however, is the following. Right? That here, so this is what is the SVD in one picture. It is always the case that there are two vectors. These that are supposed to be V1 and V2. You cannot read them. First vector and second vector, which are abnormal ones, because this is a unit circle, right? So all the points of the circle are abnormal. They are orthogonal. So these are it's an orthonormal basis in this case. Now these vectors have the property that the first one, V1, is mapped to this vector, which is how is it called? It is the well, this is the principal axis of this ellipse, right? This is the second axis, and you have the string point here. So this vector is mapped into this one, and the other one, which is orthogonal, is mapped into the other, this other guy. Right? And these two are also orthogonal to each other. Right? They are the two axes of the ellipse. So this is always to give me any matrix, square matrix. Then I can find two vectors in the domain space, which are orthonormal. If I apply A to these two, I obtain this one and this one. So these are called, so this vector V1 and V2 will be the, this is confusing, will be what later we call the right singular vectors of the matrix. The axis here, right, so these have length 1, but these vectors don't have length 1, right? But the axes have length 1, and these are the left singular vectors. Confusing because this picture is on the right, and the length of the semi-axis of the ellipse are called the singular values. That is sigma 1 and sigma 2. So this is what singular values and singular vectors are. So there are the left singular vectors, there are the right singular vectors, they are orthonormal vectors. One in the domain and one in the codomain. Then there are singular values, which are the negative numbers, and they measure the length of the radius. So that's what sigma value decomposition is. Okay. A picture. So more abstractly, so an hyperellipse is the surface in Rm, the space where the matrix maps to. Right? So number of rows in the matrix is obtained by stretching the unit sphere, right? Rn by some negative factors, sigma 1 for sigma n. No negatives, it could be 0 if the matrix is not full rank. In order to always say it's equal and some positive numbers. So the hyperellipse is obtained by stretching the unit sphere by some negative factors in some orthogonal directions, right? So here you have taken these big spheres and you have like squeezed in this direction or stretched it in this direction. So it is always the case if you take a matrix A, right, that exists is vectors V is for negative number sigma i's and this vectors U such that the image of A, the image of the hypersphere is hyperellipse obtained by stretching. Does it make some sense to you? Just think of the two-dimensional case. I think the general case is better to look at the equations. Does it make some sense?
Can you explain again the dimensional case or a summary of what you said about this axis thing?
Let's go to the next page. Or maybe the next page. This is just a summary of it. Take a sphere, apply A to the sphere, you take this ellipse, right? Or in general, you take an hypersphere, n-dimensional, you take an m-dimensional hyperellipse as the image of this hypersphere. Now the singular values are the length of the principal axis of the hyperellipse. They are more or equal. Some of them collapse. This just repeats what I said. The left singular vectors of A are in 1 through n, and the principal semi-axis of the image of the sphere, the semi-axis of the hyperellipse. The right singular vectors are A are also called the pre-images, right? The pre-images of the principal semi-axis of AS. That's it. Since this applies to a generic matrix, rectangular matrix, there are some further properties. So if m is more or equal than n, there are at most n singular values, right? The length of the principal axis, which before I made a mistake, multiple semi-axis, which are non-zero. The other are all equal to 0. If A is the rank, if R is the rank of A, as we defined at the beginning of the lectures, there will be exactly R, little r, of the singular values which are non-zero. Okay. So going back to two-dimensional example, the rank of A is equal to 1, right? Well, for example, because the second column A is a multiple of the first column, then sigma 1 will be more than 0, but sigma 2 will be equal to 0, so this ellipse will collapse to the second. The general. similar to the eigenvalues. Right? So the eigenvalues of the symmetric matrix, some of them can be zero. So equation-wise, the singular value decomposition is summarized by this equation, vector notation, or by this equation, matrix notation. So let's work with a matrix which is m times n, and let's assume that m is more or equal than n, and this is written there, and the rank of A is equal to m. Okay, so it's a full rank, right? It's a full rank matrix. So in this case, this equation satisfied. So there are n vectors Vj which are orthonormal. These are the, as I said, they are for the right similar vectors. You know they are on the left of the sigma. When I write in the matrix notation, they go to the right. These are called the right singular vectors A, the singular vectors of A. Now these other vectors Uj are also orthonormal, and these numbers, these are called the left singular vectors, and these numbers are the singular values, and they're more than zero. So there is always a solution to this equation. And this is a set of vectors which are orthonormal, and a set of non-negative scalars which satisfy the equation. It is an extension of the eigenvalue equation. Eigenvalue slash eigenvector equation. For a square matrix, we say that A is equal to lambda B. We look for all solutions to this equation, or solutions to this equation. But let's keep that aside. Let's see a bit later the connection to that eigenvalue. Here we have a rectangular matrix. So this equation doesn't make sense. But this equation instead makes sense and has solutions. Again, in 2 dimensions, I will have these V1 and V2, which are normal, right? They are mapped to these multiples of V1 and V2, which are the principal axis. So you can also rewrite this set of equations into matrix notations, and this is the singular value proposition. It's called reduced, for a reason that we will see in a moment, but this is the singular value proposition. This is commonly denoted as singular value. You can write A as the product of 3 matrices. The first matrix, U, as its column, these orthonormal vectors. Right? So the columns of U are orthonormals, and they are obtained by collecting the semi-axis of the hyperellipse. This matrix sigma, I put a hat here, but let's ignore it. This matrix sigma is a diagonal matrix which is n times n, right? And is diagonal, and as well the diagonal are the singular values. And V is the same as U, so the columns of V are what I call the right singular vectors, Vi, Vj. Okay. So here you have A, and then you put U1, UN, and here we will have U1 transpose, V, and transpose sometimes is also known as star. Since this is a it's cropped from the bottom to the star. To the cell. Transpose. So this is what the single value composition words is. So it's a way to decompose your generic matrix A by the product of these three special matrices. So we don't prove that this is indeed. You can do it. We don't prove that indeed there is a solution. There are solutions to this equation which give you the single value composition. But we study some properties of this result. Do you have any questions? These are called the reduced SPD, and we will use this view out. Okay. We can also speak of the full SPD. It's the same thing. But there is a subtle difference. Which is that now the matrix U and V, so U doesn't have the hat. So if we go back to the previous slide, a little bit. So let's go back to the previous slide. So A is M times M. Right? We have assumed that the number of rows is larger than the number of greater or equal to the number of columns. So columns, so this is now matrix. The columns are orthonormals, but they don't form a basis for Rm because they are. N is in general, N could be less than that. Right? So what you can do, however, you can complete this orthonormal set to a basis. Right? So what you can do, you can find some additional vectors, right? So un plus 1 through un, which when you add these vectors to the left singular vectors, you want to range, you have a basis for Rn. And then you can also, so what will happen when you apply A to these vectors, the result is the 0. Okay? So you can also see these additional vectors as solution of the previous equation with sigma, corresponding sigmas j equal to 0. So, this way you can write this full SPD. It's full because now the matrix U and V are orthogonal. They are orthogonal. So they are square matrices. You write A as a product between the matrix U with the M times M square matrix, which is orthogonal, obtained by completing the left singular vectors to the basis. And then you write this matrix sigma. Before there was a hat. It's the same as the sigma hat, but you add this part here, which is all zeros. You just make it correct. And V you keep the same, because in this case we assume that N is less or equal to A. And this product is still equal to A. But by writing it this way, you have two orthogonal matrices, and these are some advantages when you do some manipulations. But it is the same thing. perhaps, this is not in the notes, what is useful to also, one more thing, which is not in the notes, which is useful to take note of, is that you can also write this, the SVD, so you can also write this in the composition using vector notations. So we can write A as a sum of rank 1 matrices. Right? So how does it work? So the result is the following. So we can write A. Well, first of all, let's look at the element. Let's look at the element ij of A. So this is equal to U sigma U transpose and element ij. And then what you see is that this is equal to the sum of the singular values. So let's say the sum from k to n. We are assuming that there are n singular values. Then we get sigma k. Then we get u in ik. So you take the k left singular vectors, the ith component. Then you have v jk. So this is, so if you do the algebra, that's what you obtain. So if you take the ij element of this matrix, since it is diagonal, you can see that it derives this way. Now from this formula, what you can also see that the matrix A, right, is written as a sum of the singular values, and then you have u I, right, vj, vk transpose. Right? Sum is over k. So A can be written as the sum of k of the kth singular value times this matrix, which is the rank 1 matrix, is the product between the kth left singular vectors, C as a column, and the kth right singular vector, C as a row. Sum of the rank 1 matrices. So this is another useful way to think of singular values. These rank 1 matrices are special, right? Because they are not independent of each other. So what happens is that these two vectors have norm 1, right? But the vectors involved, the left and the right, they have the form of normal sets. So this allows you to derive further properties using these formulas. So this is a bit of a repetition, right? So you can always form matrices by taking two orthogonal matrices and then diagonal matrix. So the matrix sigma, which has non-zero elements only on the diagonal. But so this forms some special matrices, but it turns out that every matrix can be written this way. Right? And you also use the convention that the singular values are ordered. So the first is get rid of the second, and so on. And here I don't assume the matrix is full rank, so I some of the similar values will be equal to 0. Right? This P is the mean between n. We will have at most P similar values, 1 and 0. And so, as I said, there is a theorem which proves the existence. And in addition, you can show that if m is equal to 1, if the singular values are distinct, then the singular vectors are unique up to a sign change. Vi or minus vi. Model the sign change there. And the idea of proving this is to first find the leading singular vectors, so find the V1 and U1. They are the two left and right singular vectors associate the largest singular value. Then you subtract from the matrix A the corresponding rank 1 matrix, and then you iterate. We don't discuss that. So as I said, so we can try to gain some more intuition about this decomposition by linking it to the fact that A is a linear transformation, and then so we can think of what happens if we represent, say, a generic vector in the domain of the transformation using the left and the right singular vectors, and then you represent the image of this vector as a linear combination of the other singular vectors. This is the idea. So you take the vector x, you apply A, and you obtain a generic vector B. And what you do, you multiply left and right by taking a transpose of U. Right? So the orthogonal matrix, which has as its column the left singular vectors. So since you have completed this to a basis, right, what happens is that U transpose B, as we have seen in the first hour, gives you the coefficients of the expansions of P on the columns. So this is what U transpose B is. Now, on the right hand side, you have U transpose X. Then you write A, right, as single value composition. And what happens is that U transpose U is equal to the identity, so you remove it. Okay. And V transpose X instead, similarly to V, is a set of coefficients corresponding to the expansion of X on the columns of V, right? On the basis formed by the columns of V. So, and we call this X prime. So these steps tells you that the first equation is the same as this equation. And now the matrix here is diagonal. Right? So what happens is that if you represent the image of the transformation, you represent X and its image. An appropriate basis what A is doing is just a scaling transformation. So you scale just the component of x prime by the singular value, so you obtain the point. So to gain some information, now what my linear transformation A does is to make a change of basis. To make a change of basis, just rescaling of the components. So this is general case, but except I try to explain what the single value composition is, geometric pictures, equations. We have not proved that it always exists, right? But we can see that it exists if A has special properties. Okay? So, for sure, if A is rank 1, we can immediately derive the single value composition. It's easy. Why is that? Well, so if A is rank 1, as we saw before, it can be written as the product of the columns times the row. Right? And again, the range of A is the line spanned by the vector B. So here, it's very simple, because we can write A this way. We have P, we have C transpose. But this is the same as B divided by the norm of B, so that this vector has norm 1. Then you take C divided by the norm of C, take the transpose. This vector has also norm 1. And here, we put sigma, right? Sigma is just the norm of B times the norm of C. Now, here you have the same matrix, but now you have written it as a sum of just one rank 1 matrix, which is a positive number, and then it is one vector and another one which have norm 1. So these are the left and the right singular vectors. In this case, there are no others. And all the others will have 0, 0. So in this case, it's clear that if you have a rank 1 matrix, there is a singular value composition, and you immediately can find this triplet. Right? Left, right, directions, and single value. So now, if you accept that this singular value composition always exists, then it must be the case that the rank of A is equal to the number of non-zero singular values. Here is sketch. Also, what is useful, as I said already, the range of A is the linear span of the R left singular vector which have non-zero singular value, whereas the null space of A is the linear span, is space from a linear combination of these vectors, right, which are these are the orthonormal vectors that we need to add the right singular vectors with 0 singular values, which are paired with these, form a basis for this space. Okay. Right? So, the E1 and the R are paired case, right? Right, so you have that A, I, sigma I, R, is true. And then these other vectors are orthogonal to the first R, and therefore I take a linear combination of them will have a basis for the null space. This is just pretty much follow from the definition. Another interesting thing is that if you remember this, we define these induced norms, right? So you need to take a norm for range space, a norm for the domain, and then you induce a matrix norm. So in this case, so this norm is the maximum over x, and then you take the norm of ax divided by the norm a of x. Here I put the two norms. Oh, going back to this definition, somebody in the break asked a question which made me think that perhaps notations are a problem because sometimes slightly different notation means very different things. Right? So before, when I defined this induced matrix norm, I put something like an n here. Here I put something like n. So this is meant to say that these vectors are m-dimensional. This is a generic norm, this m-dimensional space. This is meant to say that this vector is m-dimensional. This is a generic norm in that space. And here, if I put 2 without the parentheses, I mean just the Euclidean norm. Right? If I put p, I mean the p norm. Then I put a parenthesis. So you need to. Sorry about that. Unfortunately, there is no. This so when you speak about abstract things, you need to realize that there are only 25 words, characters, and you run out of symbols. Right? So you need to read a little bit beyond the notation. This in fact is really good. These are the Euclidean norms. So this is the Euclidean norm in the m-dimensional space. This is the n-dimensional space. So if I choose these two norms, range and domain, then it's the case that the induced norm is just the largest singular value, sigma 1. This you can this is interesting, and you can also try to think why it is true, although you won't see it today. But the final result is interesting because we said that the image of the circle is a hyperellipse. This is always true for every given transformation, for every matrix. But now the length of the largest axis of this hyperellipse is a norm, an induced norm. Right? So this sigma 1, right, is the length of the largest axis of the ellipse. Right? Here. This quantity here, sigma 1, this is a norm. So if you take two matrices, you compute the image of the circle for the first. In the simulation in Matlab, you generate any random numbers on the circle. The way to do it, you just sample the components, right? These two-dimensional vectors, and uniform distribution, and you normalize with the contain a norm one vector. Then you apply A, and you compute the point here. So then you will slowly populate this ellipse. Right? Then you will see that there is one of the two axes is larger than the other. That's a norm. It's an induced norm for this matrix. So what will happen is that, for example, if you sum the two matrices, the norm of the sum, so that the length of the largest axis will be smaller than the sum of the largest one. Another interesting property is that that you can also form these two matrices, right, which are square and symmetric in this case. A transpose A and A transpose, right? So one is this is n times n times n. Now for these two matrices you can do the eigenvalue decomposition because they are square and symmetric. Now what will happen is that you take the complete eigenvalues, these matrices, they are the same. They have the same eigenvalues, and they are the square of the singular values of A. The singular values of A are the square root of the eigenvalues of these matrices. And this is easy to see. This is almost immediate. So because you write A as U sigma transpose, and then for example, you put A transpose, you have U. So you take the transpose of A, so let's do this step by step. Okay. The transpose of A. So then we use the cyclic property. We take first the transpose of V, which is V, and the transpose of sigma, right? And then the transpose of U. This goes away because it's the identity. And this becomes U. This becomes a square matrix, sigma sigma transpose. On diagonal as the square of the singular values. Sigma 1 square, it's n times n. Transpose. So indeed, these are the eigenvalues of this matrix. If you do the other thing, A transpose A, you get the same result, V in place of U. So, and the other thing, last thing, is that you can also do the singular value decomposition for a square matrix. Right? It applies to any matrix. Let's do it for square matrix. In particular, you can do it for a square symmetric matrix. In that case, we know that the eigenvalue decomposition applies. Okay? So you can write A as Q lambda Q transpose. Q is the orthogonal matrix, and lambda is the diagonal matrix. The diagonal eigenvalues, positive or negative. So now what happens is that in this case, Atlantic, you can always rewrite these as U sigma V transpose, and you take the singular values to be the absolute values, the singular values to be the absolute values, the eigenvalues. Right? Okay, so you can write these as Q, right, sigma, and here you will put V transpose. The columns of V are the same as the column of Q, but when the eigenvalue is negative, you take the negative of all the components. Okay, so we stop here, and next week we conclude this lecture and then cover this class. See how the idea is.